I'm starting to realize that without them, I cannot move. So now they are there. You, you're actually waiting and saying that we cannot go live or rather online without you. So you are the, what is that called? Guiders for us to move. So, I think, we'll just continue. Uh, so now here you see so if you have done with this now, so you may ask the question. That's exactly the question you are asking. Is there same, right? So, can I change? Yeah, I mean, now you can change. So you can say 2660 and the next one is 9368 and the next one is 0632. Then you have 5664. And then you have 0632. And 4816. And this is 1 3. So I copy 1 3 and put that into 3 1. This is 1 2. When I put that into 2 1. And this is 3 2. But that's pretty same. So I copied the 3 1 and I changed it. And this is 2 3. So that will be the same as 3 2. So now I have 2660. I copy that onto this one right here. And then I have copied this onto this one right here. So within a fraction of maybe 30-40 seconds, your matrix is done. So these are not very hard. Just to mention. Continue with the second iteration. Just helping and starting people who have not done. Any questions? You're good, right? You can do the second iteration. Hmm. Hmm. So error will keep going down, and then you can stop when. Yeah.
My question is how I will get the error equation because after solving I get the matrix V22.
So you did after V3 you calculated V3, right? The V3, and then after V3 you calculated. You are getting, you are backing calculating the V1. Uh,
The last line, sir.
so this node, so this is done.
Yes,
So
sir.
once you are done with the node 1, now you are going to find out the difference between the V2 that you calculated first time and then V2 calculated next time. And that's basically your error. I mean, whatever you call it, error maximum.
I have calculated V22 just above that line.
So V2K plus 1 is V1 minus Z12 I12.
I have calculated that.
You did that?
Huh.
Okay. So that V2 that you calculated, V2K plus 1 is V22. The one you are calculating is this.
Yeah, I have calculated that.
And then you have the V2 that you have already done from the first iteration.
Okay.
So that V2 from the first iteration is
V22 such now. Maximum value.
Is this? So what we did was we 2400 see 2400 zero. We said 2400 zero is the voltage on all the buses. So all that is actually our guess, right? I mean we know it's not true. So you 2400 that is zero. You are putting in V1, V2 1 and V3 1. That V2 1 is 2400 zero, right? So V2 2 is new that you can. So you get an error between V2 2 and V2 1, which was 2400 zero. From the next iteration, it will not be 2400 zero. This will be the new that you calculate. So you got the V2. That is what we call it as a V difference. You see that? Understand, right? That's the error. Now that error you are not taking anywhere. You are not adding anything with the error. That error is just to check whether you want to stop or not. It's just a stopping criteria. So what will you do to the next time? We know that we cannot use V21 because V21 minus V22, the error is not zero. So what will you use? We will use V21, V22. And so you use 2371, 76, that matrix to update the next voltage. So for example, you take that number, they take that number and find the drop to get V3. So first we said V1, V2, V3, they are the same. Now you are getting new V2 and new V3. You should do it. Don't leave the code. Go. So after you do the first iteration and the second iteration, you will be now getting new values of V2 and V3. Do you have new values of V2 and V3? Not exactly the same number because of it, but you have two new values of V2 and V3. Yes? How many of you have new values of V2 and V3? New values of V2 and V3. V1 and V2 and V3 was 2400 before. Right now, V1 is 2400, V2 and V3 should be different. If you have gotten new values of V2 and V3, you can raise your hands just to get a check. Not yet. Okay, take your time. Oh, here's the thing. MATLAB takes radians, not degrees. For him. MATLAB takes radians, not degrees. So when you say cos 120 and J sine 120 for the voltage, you have to convert that 120 into radians. You did that for the first that could be the problem in the number. Carson diagram could be still you cannot judge it like two radians are actually pi divided by 180. So you do 120 times pi divided by 180, and I'll try here. So I just thought about it now. So could be the reason. So you did you get V2 and V3 also. Oh, very good. That is it. It's going down. So the winner is here. There was a race, and unfortunately, whoever was leading first is going down, and the winner is I don't know names, but the winner is the group here. And you can continue on the third iteration. I mean, do you want to try put a for loop and see? I don't know whether you are interested to try a for loop. You could do for I equal to 1 to da 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 and see whether just if you want to try, you can try. Or you can possible, then do the magnifying. It will be visible to all. Oh, so yeah, that's okay. I'm just playing around with that. Okay, so second iteration. I think you completed second iteration. Anybody else has completed the second iteration? Not converging, it's diverging. Error is increasing. Error is not decreasing. Error is increasing, decreasing. So one to one. If the diverging group is more, then I will intervene. Should be some bug. I don't know whether. How many of you completed the second iteration? Oh,
Like define red one, red two, red three. So radian to convert it in radian, LBM equal to 2400 cos Z1 plus sin Z1 into I by V2 and well, Z1. Good. Now V2 equal to V1.
and make sure you are consistent with notation. You have a big V and small v. So V3 equal to V1. think V is yeah. When you calculate the based on the load and the voltage, calculate the current. To have the load also. So, plus minus 120 plus sine minus 120 J cos plus 120 plus sine. Yeah. I think the 120 MATLAB don't like degrees. MATLAB only like radians. So you have to convert 120 to radians. So 120 is equal to, in radians, is equal to 120 multiplied by pi divided by 180. So you can write something here. So what I did there, I call it radian 1, just, for is equal to 120 times pi divided by 180. And I call it radian 2, minus 120. Oh no, 1 minute. I think one is minus 120 times pi divided by 180. Make sure it is consistent. So this is college radian 3. So now I can do cos radian 2 sine. We don't want radian 1, right? Radian 1 is 0 because you already know 2. Then you can say radian 3 and sine radian. So now we are consistent with converting into radians. So your V1 is done. So now you can go and then say V2 equal to V1 and V3 equal to V1. And now you can start as the load. Write down the loads. There are two loads as the load. Yeah, as the load. Uh, so there are two loads as load. You can see, right? Do you want me to zoom in? Zoom in. So if you are, how many are done with second iteration? Second iteration not done. Second iteration, you want to go a little further and do third iteration. Just take it easy and then. For the second output. Oh, that's a nice idea. We can put that into for loop as an assignment. Let's see how I can challenge. And I can guarantee that if you complete that, you will get a credit for your third semester power course. If you don't do it and then if your computer course closed, then you will not get the credit for in the third semester. If you do it now, we will tell them give credit to the third semester. You don't get power course you're going to take, right, in the third semester. Yes. For that, you should show that you can solve power flow. There's one thing which we always say that you should stay away from. That is your tendency to not to do things. Keep doing. You should not stop. Well, I tried to do this. Okay. Second iteration. Still working. How many of you have completed second iteration? It's going down. You want help?
We have initially V1 equal to V2 equal to V3 equal to 2400. So, then this voltage is 2400 plus I into Z. It will be greater than 2400. Then it is also greater than 400. If 400 just cost distribution after the third iteration, we got value of 2437. Again, when we assign this to here, then the value got increasing. So we are not
Not assign that here.
we can't.
No. So this one made this high, right?
Yeah.
2437. So you are actually wanting this voltage right here. So you have two options. You have to keep this voltage constant or this voltage constant. Yeah? If you want to have this voltage constant, this voltage has to go down, right? Then only you make this voltage constant. So what you do is that you look at this voltage in here instead of 2400, that will be down, right?
Yeah.
So your 2400 has to be here, not here. So you use the 2400 here to calculate this load. That is why this is going up, right? Understand? So this has to be down. So whatever you are seeing here, if it is up, you have to decrease this voltage. So what we will do is we will we have well, I think only one option, not two options. So we will give this as a take-home assignment for you, which you can solve because you already got an idea what to do. So try working with MATLAB and solve it and then bring it back tomorrow. How many faces are liking that? Some faces are saying, let's try. And what we will do is, if you have done this two iteration, and if you are excited about it, you can start putting that in a for loop. This so, but this is actually there are two purposes for it. One purpose is obviously trying to see whether you can complete an assignment. Number two purpose is if you are in this area, this is a must, meaning you have to work on some level of coding in MATLAB, not necessarily this power flow. Any power flow you must do. It's a fundamental thing. So I remember when I was in the master's program, I did my assignment was developing power flow, scaling it up to 1000 bus. Then you go optimal power flow, scale it up. Then you do transient stability analysis, scale it up. This is actually a part of um, I'm not saying that you should do all of that, but at least to get an understanding of how to freely work with the MATLAB. So, so it serves two purposes, right? I agree that they can. So that's something which you will do. I will turn your attention to next 30 minutes or so, or maybe another 30-45 minutes or so. I will turn your attention to optimal power flow. Okay. So there are two parts that I think you should be doing as a must. One part is to solve the power flow which we are giving as a distribution. Another part is solve the power flow for transmission system using Newton-Raphson. I gave you an example for a 3-bus system. Then the third part is to solve the power flow for transmission and the distribution system combined. What we call it as the co-simulation for integrated transmission distribution. So those three assignments are actually ideally you should do. So you'll get a good grip of what you should work on. But as a first step, you can dream about it, but as a first step, let's do this forward, backward. I think this is pretty reasonable, right? You understand how to do it. It's not that big task to do it. Yes, agreed? Okay. So what we will do is I will show you something on optimal power. So optimal power flow, we learned about it this morning. And optimal power flow is basically doing power flow in a different way. Remember, doing power flow in a different way. How do you do the power flow in a different way? You run power flow through optimization routine. Okay. So in the morning, we talked about the main pieces of optimal power flow. Optimal power flow consists of optimal power flow modeling consists of an objective function and a constraints. And constraints can be divided into equal constraints and inequality constraints. So, and then we said that we have optimal power flow can be solved using mathematics solver. One way of solving is by using linear programming, where you run the linearized version of the power flow equations. Then you can run it through nonlinear programming, where you run the power flow equation using quadratic equations in that form, or a higher quadratic equation. And the third one you run through fixed integer programming. That's another way to do, but you also run through what we call it as convex optimization, right? So what I am going to show you is some small way of running the code for a small system for an electric distribution network. So this is an electric distribution network. This network is a part of an IEEE. Okay. How many of you have heard of IEEE test systems? Few people have heard. Very good. IEEE test systems are systems that academics uses in general to study an electric grid model. They are systems that is developed by a group called IEEE, it's Institute of Electrical and Electronics Engineers. They provide power grid models that you can use to study analysis of power grid. It can be power flow, it can be optimal power flow, it can be dynamic and transient stability assessment analysis. These power grid models are actually not fictitious. They are real power grid models. The real power grid models are modified or aggregated or reduced, keeping the characteristics of that real life system and developed in the form of test system. So, which model and which part of the world these test systems are available? You can see that by looking at the IEEE test system library. IEEE test system library, you can Google and search IEEE test system for power distribution system model. You will get a link which has got a lot of test systems that you can use to study power grid model. So these test systems are characteristics test system to study specific phenomena, right? For example, oscillations, dynamics, things like that. So when you are trying to develop a problem as a project or as a research project or something, you first use this system to test these problems. Some of you are maybe aware of this also. So IEEE test system for a power distribution network, one of an unbalanced IEEE test system which normally we use to study electric distribution network is an IEEE 123 node test system. 123 node test system consists of a substation like an LTC, regulators, and main feeder and laterals. There are several nodes in the 123 node test system. 123 node means what? The test system has 123 nodes. That is why it's called 123 node system. This is a subset of the 123 node test feeder starting from substation. So this is a substation. This is a load tap changer transformer. This is a switch that connects this where the feeder starts, and the feeder goes all the way like that, 120 test node. This test node, we have some of the points where you have connected PV farms. Okay, so these PV farms are connected to study the DER, integrated distribution network. So you can study that distribution network like that. So the first 20 nodes from the IEEE test system is extracted and shown here, which are 5 PVs are placed, 50 kW on bus number 5, 70 kW on bus number 8, 100 kW on bus number 13, 150 kW on bus number 15, and 50 kW on bus number 9. Okay. So you say these are placed. These are placed means what? You place them. How do we place them? We'll talk about it. Because go ahead.
Numbering, how the numbering are,
Uh,
how the numbering are done, like what?
Good question. So this okay. So there are one tell you some. So real life electric grid um, is probably here too, but real life electric grid doesn't have numbers. It has only names. So for example, you know, whatever the names we have, Prayagraj, 1, 2, 3, whatever. So when you study a power grid network to study for power flow, you cannot use names. You have to replace the names from the into numbers. So what you do, we call it a bus numbering system. Now, why you want to do numbering? There are two reasons for doing numbering. One reason, if you get a numbering, you have an idea about what are in sequence, like from substation all the way to the end, what numbers are in sequence. Second thing is, if you want to run an algorithm for power flow, for example, you have to run in a for loop. You say 1 to 35. You cannot run 1, 17, 55, 30 or so. So this is called bus numbering. Who does that numbering? Basically, we does the number. In real life, there is no such number. IEEE test system will give you numbers in a sequential form right from substation to the last point. So these numbers are done from substation to the last point by the test feeder system itself, which means you can just borrow the test feeder and run it with numbering. You don't have to number it. What happens if you have some numbers given by somebody or names given by somebody which is not in the order? Then you need to run an code to, we call it bus renumbering or bus numbering code. So what does that code does? Code actually scans through, if it is even a number or a variable or a name or anything, you can run code like for example C or MATLAB using a function called fscanf, which is basically a function to scan the image, and then you can create number out of it. Long story short, this is has to be renumbered from 1 through 123, and that's done by the test feeder itself for this system. That is actually because it is numbered based on distance, actual distance. So that is done through the distance will be more. That is why it is there. Yeah, physically, right? You don't know because it's drawn like that way. It's that is you cannot judge that. You draw, you can redraw in any way you want. You can make this longer or shorter.
And it's
Hard to.
Indian northern region, there is 273 bus system. So buses are means quoted in terms of numbers. They are actually places, as told by sir. So 273 bus system is a very large system. So in order to just analyze the change in number.
Answer renumber and change. So you cannot correlate. Suppose you are thinking, so you did not probably think through all what I am talking about. You are thinking just looking at this, see why that is nearer and why that is far, which is also a good thing that you're thinking like that. That's you must think, and we also think like that. So don't worry about that thinking. But what I'm saying is, it's very hard to understand from physical appearance that whether it's near or far. So what you do there is you do Well, I'll come about that later. So there is something called, you can do a search, depth search or breadth search based on a distance, and you can actually get number based on that. So we'll talk about that later. So this is something that you have sitting there. So MATLAB has got a tool called live script. Live editor or live script is a tool that you can use in MATLAB to live talk about how the code runs in MATLAB. So what we are going to show you is two things. First, we are going to show you how you model the system. I don't know whether you can you see at the back, or can you see these numbers? No? No. But you don't have to, you have to, so any device, any system, you organize the data of the system to run the power flow in two forms. One is called bus data, another is called branch data. Bus data is to give you the bus number and what is in that bus, and branch data is to represent how the branches are connected. So this is something called branch data. Branch data, everybody know bus data, branch data? I think some of you already know. Okay. So branch data means that you connect the bus or branch between buses, and you see this branch data consists of from two, node 1 to node 2, 1 to 2, 2 to 3, 3 to 4, 4 3 to 5. These are node connections. These are resistances. AB, AC, BB, BC, CC. So we have resistances. We also have reactance values. For the resistance and for the branch. And then you start having bus data. And the bus data, you will use the QL. PL means load. You see load information. You can also the PV. PV means photovoltaic. And you see the PV load. So you said that I have put to the PV implies the PV. What am I doing here? Saying that the PV is there. I'm going to put the capacity of the PV right there. Good. This is how we do the load data and PV data. Do you understand what this is? I will let you read through rather than me speaking. Some comments are there, so you should be able to understand. What is that? Do you know? Can you see? Can everybody see? What is base? What are we doing there? We are converting everything into per unit basis so that you can actually use the run the system without having. So that's what that topic, that part is. So then you start representing this in the form of a graph. So if you put it in the form of a graph, you will get a uh, Yeah, so that is something you can actually represent. This is basically in kilowatt. So what we have done is you can utilize the data set and then represent in the form of kilowatt or watt. Depending upon the base, you can make the kilowatt and you can make the watts. If you have a 1000 MVA base, you write it and then you put the number there, then it will be 0.5 per unit based on that. So basically the load and the PV, the data that you are writing is whatever the kW you write in that values. So is forward. So there is a little bit of, it's a very good thing or question or comment also. There is a little bit of creativity you can use here. You can utilize whatever way you want until you get into per unit system, depending upon how you want to think about. So modeling wise, you have some flexibility. Now this represent how to generate the, based on the from bus and to bus, how to generate a tree like structure for the distribution network. I am not able to discuss the code and then run at the same time because I have to move the screen. I will run and then I will show you how that thing looks like. The next one is so these are defining incoming and outgoing branch. So you have to run, if you run a code, you have to provide incoming and outgoing branch connections. Right now we are hard coded it, meaning, everybody know hard coding means? No, okay. Hard coding means putting a number and then using that number for your purpose. So that's basically based on case to case basis. Okay? Generalized code means, so for example, if you go, okay, V3 is S3 divided by, then you say V2 is S2 divided. Okay, next time V3 is V3. So these are hard coding. But if you put, okay, 4 I equal to 1 to n, P3 is, that is not hard coding, that is generalized, basically. I think I mentioned about it. So there is a word that it is hard coding, meaning just putting constants and number there to run something. Hard coding is not an effective practice in general, but hard coding is very good for troubleshooting. Otherwise, in a scaled system to do, you cannot know what's going on with it. So these are number mentioned, which is kind of hard coded. So now you have to mention you have to put the impedance matrix and H matrix. H is something that in convex optimization we call that as Hermitian matrix. So you might have seen this word coming while I am talking in the theory. So you have to develop a Hermitian matrix to move it in the form of convex optimization. So the H matrix equation you see here. Why am I showing this? To just show you that whatever math that we did in the morning and talked about it, same thing you are converting into code. Nothing fancy here. So the H matrix that you have has a math like that. So I cannot put the slides and the code and the result all in one. But if you look at the slide that I discussed now, I'll go through that. You can look at it. This is the equation for H, Eij and Qij, Hermitian matrix for P and Q. So you can actually represent that Hermitian matrix in the form of math that is written in here. This thing 2 times R, 1, that is basically that right here. So you can write the code. So I'm not going through that code part, but I just wanted to connect you with what each part looks like. Now we can actually have a load PV information. Load PV information is basically to tap what are the values of the load and what are the values of the PV. So this you will get a little bit more clarity on some of the questions that we have here. So this is a P load that is taken from the node ID 123, which is written on the top. Then you can actually get that load information and you can change the load like a multiplier. So for example, if you have a multiplier 6 PMP1, you can actually have a load change. You can also get the PMP in here. And then you can multiply that load into base MVA, 1000 and kW, depending upon how you are representing the load. So right now it is in kW form. So you multiply based on that kW. And then you can do a load apparent power. And you can actually size the inverter. So I don't know whether you remember or not, the inverter reactive power is calculated based on the load, the PV load. Q is equal to square root of S square minus P square. You have a equation that we discussed. So you can actually use that equation in here, and you can also rate the inverter size more than the PV capacity. Okay, depending upon how you want to put the inverter. So now we have completed setting up the system information or the electric grid information. Now what we will do is we will start writing the code in optimization form. So somebody was talking about optimization routine, and they were asking me, or rather I was asking Paresh, I guess, was talking about it. So I was telling him about using optimization and optimization solver. So optimization solver, actually you buy or you get some license. Some of the optimization solvers are like Cplex and some different type of solvers you buy. And there are some optimization tool or software that you can run, which is some of the software are pricey. So I think he was mentioning he's using GAMS. GAMS is, I think, pricey software. So there is a tool which can be used to run optimization in MATLAB, and that toolbox is free. So you can download that toolbox free of cost, and the name of that toolbox is L05. Okay, so if you go to search, I'm not going to digress it from here, but if you can search for YALMIP, you can get a tool developed by one group which has got a installation software that you can install, and that YALMIP installation, if in the same, it runs in MATLAB. So you can run several solver in the YALMIP tool free. YALMIP. YALMIP is the name of that toolbox. So that you can download it. It's a zip file. You unzip it, put it in a path in MATLAB. You can run many optimization solvers are free, except for some of the optimization solvers like Gurobi. Maybe Gurobi is also free. I don't know. So try the software. CVX is another group that is only used for SDP kind of a software programming. CVX is okay, but CVX, I think you have to, if you run a long code, you have to upload it to somebody and they will solve it and give it to you, or something like that. So it's a little tricky. This one is you can use. I suggest we had a lot of fun with this tool. There is a other tool software, optimization solver that is not available here. You can get academic license. I think one or two, either Gurobi or some is not available here, but you can download. Yeah, so you can go to YALMIP and then get it. Okay. Yeah. So I mean, we can talk about it and we can use it. We'll talk about it later. But just so if you do that, you will get a optimization variable can be used using this function called SDP var. SDP var, you can write the node voltage, complex branch flow, slack, power bus, and PV reactive power. So, and you initialize that, and then you're ready to run the optimization. Okay. So, what is the optimization that you can do? You can solve the optimization using an objective function. This is the objective function, sum of voltage deviation of all the buses and the phases. So, this is the objective function. So, this equation is written here. So, the next equation for the constraints is the power balance. So, this is power balance equation. So, constraints can be written for the power balance equations. So, you can actually write power balance, voltage drop, and voltage bounds. So, you can go ahead and then develop the constraints for power balance. So, this is a constraint for the power balance. You are writing the constraints independently for each node. So, this one doesn't have an upstream branch, this one no downstream branch. So, you write that. And so, every node you can write it to do the constraint for the power. This is a constraint for the inverter reactive power limit. This is a constraint for the voltage bound. You see the constraint 0.95 to 1.05. And constraints for each branch, you can actually do the voltage constraints for each branch. So now our constraints are done. An objective function is done. Is that speed okay? Do you understand? I'll stop here and ask questions. Any questions? You understand? We can. But 20% are normal because 100% is actually almost double the cost. Normally, people try to overrate the inverter a little bit, not beyond that. So that's why I kept it as 20%. You can run for any number. It doesn't. Real life says that reactive power support that is required in a specific node by any device is 30% times the active power flow. 20 to 30%. It's just a rule of thumb. It's not. So we are ready to solve. Solving optimal power flow is optimizing with constraints and objective function. And these are the voltage that you collect. So what do you get? How do you solve the optimal power flow? You solve the optimal power flow to find out for an objective, right? The end you collect the voltages and you plot the voltages and see what is that voltages. If the voltage is not bounded, that means the solution is not feasible, whatever you are getting, right? So the indicator is basically the voltage. The voltage is plotted in here. So now you plot the voltage, you have a challenge. The challenge is unlike transmission system, when you plot a voltage, you will not get a voltage in every node. So if you have suppose 3-phase node, you will get voltage in all the 3 phase. And you represent the 2-phase lateral, you still need the 3-phase nodes to represent the voltage. So one phase is not existing. So you have to put some number, otherwise it gives MATLAB gives an error. So you put an NaN or some number to represent. So you see a bunch of those kind of things in here for each of those phases. And you can compare that with a base case. What do you mean by base case? You can run an optimization algorithm or optimal power flow without having any objective function. If you no objective function specifically created or zero objective function created, the optimal power flow should run much like a power flow. You should be able to get the results from the power flow. The methods are different. One is optimal power flow, one is power flow. They're not physical laws are not abided. You're artificially creating physical laws in optimal power flow. So you want to make sure that it is exactly the same as a power flow. So that's another benchmark you do with optimal power flow. So base case situation means that you are trying to run the optimal power flow without any objective function condition. You just see whether it satisfies with power flow routine. And then you can plot. So now we'll do two things before we go to run this. One thing is review one more time your optimal power flow routine. So you can see that the optimal power flow we talked about uh, the three different variation. One is when the losses are ignored, and that is called linearized power flow, linearized distribution power flow. Then the next one is you can run that through relaxation models. Then you have two convex part. One is semi-definite programming, and the last one is the uh, second order cone program. Remember those three? Okay. So that being said, we will now go and look at the how to run. So you can actually run this, what we call it as a live script. So if you run it as a live script, you can uh, run in different places. You can click the run button in here. So the first diagram that you will see here is the uh, branch. So you see the branch, how that are connected based on the branch representation. This is the connection pieces for the optimal power flow. Good. Can you see? Okay. All right. This is basically the branch connections, and you can say you can see whether it's successfully solved. Yes, it is successfully solved. This is a solve time. This is actually the time that is taken by Almip, and this one is giving that successfully solved with a solver called linear programming, and the element wise distribution of constraints. How the constraints are be taken, and coefficient rating associated with that. These are some metrics for the OPF, and you will be able to see the performance by looking at the voltage profile for all the three phases for the 20 bus with and without the optimization and comparing. GAMS. Yeah, yeah. We can use MATLAB optimization toolbox. We solve it using MATLAB optimization toolbox. But MATLAB optimization toolbox is very restrictive. It is not a convex optimization toolbox. It is more like a generic optimization, linear programming, non-linear programming, that kind of toolbox. What we are doing using this tool in LMIP is to solve through using convex optimization. So convex solvers, it's like a little bit more math there, but in general, convex solvers are can do things to convexify the equations that we are giving. For that, the solver has to really understand the equations and then convexify. And that's not possible using MATLAB. Many solver in MATLAB. There are several tools. So convex optimization toolboxes are very few. I think GAMS is one of them. CVX is one of them. The LMIP is one of them. These are toolboxes. Toolboxes are different from solvers. Solvers are generated by companies like a Gurobi, Cplex. Tell me some names. I'm blanking out some. Cplex, Gurobi. It's only two things you know. There are some 8 or 9 or 10. Or yeah. So GAMS, YALMIP, CVX, they are toolboxes. They are not solvers. Solvers are solvers, which actually solves optimal. I think there are 8 or 10 of them, which are convex solvers. Non-convex solvers are many, like linear programming, quadratic programming, sequential programming. So SQP solver, all those non-convex solvers you can use in MATLAB. So there are convex solvers. There are, I think, several items, not just Gurobi, Cplex. There are a few others too. Just to give you a landscape how that is done. So this is similar to that. This is a convex optimization for that same feeder right here. It is done through SDP. So this is the line info. That line info is completed in here. Then you have per unit conversion, connectivity matrix. You have modeling of regulators. Regulators are modeled with the tabs, which you can see right here. Then you can define the variables, complex power, Hermitian matrix calculation, active and reactive power calculation, minimum value, maximum value, and now SDP. So the same problem, that same power grid that we have for solving, now we are solving through SDP. SDP is semi-definite programming. So you see the equations for SDP. These equations are actually the same equations you see on the slide. So you will see the constraints calculated for each one of them. And SDP constraints, you will see that is written here for single phase lines. So every line you are writing the constraint. Then this is a power balance equation. So you have a line power balance equation written for every line. Voltage constraint for slab bus. These are the voltage limit or bound calculation for every line, power limit calculation for every line, and then objective function. Objective function, my famous solver, Mosaic. That is the third one which I'm adding to your list. There are, I think, I said 7 or 8. Mosaic is the one that is used for SDP solution. So you see the SDP cost is loss, constraint, loss, SDP setting, solver, and mosaic. So you are going to solve this using mosaic solver after you set it up. And the objective function is cost, which is loss minimization in this case. So now to minimize the losses, you have to calculate the line losses. So this is line loss calculation, calculating the substitution power flow and plotting, and then plotting results. So this is SDP. So you will see the branch data, and then you see that this is not solved because you didn't see the solver mosaic. So the system is not solved. So if you want to solve this SDP, then you need to install the solver mosaic. Mosaic is actually not a part of YALMIP. I think you need to uh, buy it and install it. So that is what it is. It looks like I have not installed it in my this laptop, but you can run that. So let's see if I can run the other one. This is the second order cone programming. Another solver, number the fourth one, is called cone PROG. It's called cone PROG is used for second order cone programming solver. So the cone PROG solver is available in here. So solving cone PROG with the solver time, optimal solution reached for the because of the after a successful solution from the solver. So you can see in the SOCP formulation, this is the SOCP formulation. It's basically coming from the what. So in the SOCP formulation, you can actually see constraints limit for DER, voltage drop constraints, power flow constraints, extract constraint, and so forth. And you can see that the with and without DG, how the optimization value is in, how much the power loss has been reduced with the optimization solver. We can see it like that. So I'm doing this most like a show and tell, so you will understand what we have done and how to model that in the convex optimization. So I'm going to stop here and ask. Oh, I wanted to give credit to a couple of other group members we have in our collective group. This part of this optimization work is also available in IEEE repository. It's called, we conducted an IEEE tutorial on the optimization with two other professors. So it's teamwork, and acknowledgements are in here for those team. And if you want to do more detailed understanding, you can also refer the tutorial that we have, which is free of cost if you are an IEEE member. I don't know whether, I think most of the people are IEEE. So you can go ahead and search in my name, optimization, convex optimization tutorial, IEEE PES. And if you go to IEEE PES, you search for convex optimization tutorial. So we have a 3 faculty member group and few students together. You can see that this is not a one-person job, so we have developed it together. I will give you some part of this also, not this, but the one which I developed my own. I'll give you a part of that for you can use it as well. So you can distribute it for a small system. Uh, but I don't. If you are if you practice, then you will be able to see it. But I don't think you can build it here because it takes some time on the convex optimization. But I think the other power flow you can they can run it as an example. Any questions? Any thoughts? Yes. Go ahead.
Then, yes, here the losses reduces just half. Yes, it reduces means half. What other optimization one can use to reduce more losses? This recently, yeah.
Along with the losses.
Yes.
So this objective function is just losses minimization, right? So that loss minimization is the objective function. It is minimizing the losses. Now, can we use another method or another optimization
Question
to
is that
reduce
we
more
can
loss?
reduce more losses further with the other optimization, means where
So
we can.
convex optimization is global. If it is a global optimization, you cannot reduce the losses beyond that. That's basically the global optimization. So it claims that is globally optimal. So it's obviously making it global optimal, finding the global optimal point. So you cannot, you will not be able to get beyond more than this for that. Well, so sir, there are so you're talking about objective of loss reduction. Losses can be reduced by several ways. Losses can be reduced on an existing system just by changing the set points, which is done by optimization. So optimization doing its best based on the existing system. You can also reduce the losses by having photovoltaic in every place, which can supply the load good in all the places. So what happens if you have a photovoltaic here and it supplied the load there? Another photovoltaic here, supplied the load there. Will there is a need to have the power come from substation to those loads?
Yeah.
If the power is not coming from substation to the loads, what happens to the loss?
Automatically reduced.
Can you make the loss zero if you do it every in local point? Yes, you can make the loss. That is not a part of optimization. That is a part of having resources allocation in different points. How do you arrange the resources allocation? Can you ask the photovoltaic to do that if you are having existing photovoltaics and do the best? You could do that. You don't need optimization for that yet. I mean, some level of optimization is something they could. So there are different strategies to do this. But as far as given problem is concerned, if you are using bunch of optimization tool, convex optimization is considered to be, if you do it well and you have a feasible point, it will give you global optimal point,
Yeah,
which
that's
means you cannot do.
for
For that,
same problem.
that is it. Yeah. Well, you cannot do. Yeah. So if your question is that the only way to reduce losses? No, because there are some other ways to reduce losses. You understood that. So this actually gives, so SDP does pretty similar close by close results as opposed to SOCP, which is another way that you can use. So that is why people talk about these kind of optimization technique. Even though you can see the intensity of math there a little bit, you might have gotten the taste because it's not, you need to really understand some of the things which I cannot even. So what is a Hermitian matrix? What is the property of that? How do you develop? That's actually is a course or this optimization thing itself is a course by itself, right? You cannot, so if you want to go deep in that. But what our goal is for this GAN course is to give you a flavor of what are the things that you can, so you touch base with. So we are not going very deep in each topic if you may look at it that way, right? That is the whole idea.
So what are the fundamental difference between nature optimization as well as normal?
So if you are looking at, for example, swarm-based optimization, or there are what is the other one? GA, genetic algorithm based optimization, all that. When you are doing those type of optimization, we call that parametric optimization. Parametric optimization is a method that is done just by optimizing the parametric space. Okay? That optimization do not know about electric grid, do not know about physical constraints, do not know about nothing is modeled. What is just modeled is taking the parameters, finding out an optimal phase for the parameters. Now the generation of that parameters is up to you, how you generate the parameters. Can you generate the parameter using a power flow? Yes, you can generate the parameters using a power flow. And you can say, this is a parameter that I generate. Now you get this parameter into point from one point to another point which you consider as optimal. So that black box or whatever that soft computing method is going to give you a parametric space, bunch of parameter in this space, finding out the best parameter given a condition and then giving back to you. So that is a completely software that is not knowing about physical property of the system. If it is for used for optimal power flow, if it is for energy market, if it's for anything, they are just using the parameter and optimize. That's basically what the soft computing methods does. So that method, because of that nature of that method, those methods are not mathematically involved, in the sense that those methods are not writing the physical equations of the power grid and writing all the equations and conditional laws of the power grid. But they are challenging in a sense that you need to find the optimal value in that search space. So in that level, it is important, it is challenging.
Sir, one more question from my side. Considering the UK.
Yeah. What should be the property of a good optimization method? Because we may use different optimization methods. When suppose for optimal power flow, what should be the required property for a good optimization flow?
Required property of the code optimization tool.
Yeah, optimization tool. Because suppose everybody is claiming that my optimization is better than other optimizations.
Oh.
So on what basis we can just decide this particular fact, that what should be the property of a good optimization tool, so that I can pick from the beginning?
So the very good question. So as far as a physical power grid, for example, is concerned, when you are going to look into the end result, the tool should be able to give you the end results considering the real life scenarios. That is basically should be the best property, and then doing the best job considering that scenario. So for example, if you are going to use a tool, a code or tool that is actually, so there are different pieces in an optimization optimal power flow method. If we are using in this way, there's something called a tool, there is something called a solver, and there is something called a model. So these are modeled based optimization. Now if you are using a parametric optimization, there is something called a tool, there is something called a parametric search space, or maybe sometimes a solver, sometimes even not a solver. That's parametric optimization tool. The model based optimization tool, there is a model, there is a solver, there is a tool. For example, all the optimization classes which you have a model based optimization belongs to that category. Parametric based optimization is just a parameter optimization. There is no model associated with it. It can be used for any system, like process system, or anywhere you can use particles optimization, things like that. Any tool that you are using for optimization, that tool by itself and the solver by itself cannot complete the job. You need to have the description of the process or the model. So the requirement for the tool for us, for example, in the power grid sense, it should satisfy the power grid laws. It should satisfy the power grid uh, constraints or power grid setup, and it should give you the best optimal results for that specific problem. That is the best tool, best framework. I don't want to use the word tool because tool, solver, and model together you call it as a framework. For that to happen, you need three parts. All the three pillars are important. One is you need to have a very robust model. That model takes care of the physical laws of the power grid. So, for example, you need to have a constraints, voltage constraint, power constraint, thermal constraints. All those things are a part of the model. The second, that same model should be able to translate the power grid into the tool, and the tool understand that translation. So, for example, power equations, you're translating that into cone equation. Tool don't know about anything about power equation. So all these things are done by model. So what we have to do is basically develop that model and make sure that model satisfy electric grid on one side, and the other side translating that language to tool. The tool can understand. So that's what we call it modeling. And after that, the tool should be able to solve that problem using a solver, and the tool should be able to get a result that is possible to get a result. For that, the tool needs two things. Tool has to get a result in combinatorial time, which means you don't get the result tomorrow. It has to be done in whatever. Second, the tool should be not be giving infeasible, meaning when some got stuck, it's not solving or something. That's the tool's job. Model's job is to make sure that whatever results which is coming out is making sense to the power grid, like voltages are within the limit, voltages. So a tool that is successful will have mathematical feasibility and then real life feasibility, the framework. So mathematical because you're real. So that's basically the success story. Now, how do you know that mine is better than yours? After the success is done, my result that you get, for example, 50% loss reduction or whatever you get, that should be the best loss reduction that I get compared to all the other framework that you have. If you can claim, that means my tool is the best. Now that bestness or the criteria of best is dependent upon state of the art, which means what others have done. So if the maximum loss reduction is 49, I get 51, that means mine is the best. How do you know that that's going to be the best in your life? That you have to prove through, for example, global optimal point like optimization gap, and there are some criteria for doing that. So that's basically the tool with the model. Now, parametric optimization tool. Many people claim that this is good in the soft computing world. Unfortunately, there is no model associated with that. So how do you make the parametric optimization tool exactly like this framework and the model-based tool, and then say that it's better than the model-based tool? First step for that is this parameter space that you are developing or parameters that you are generating should come from a model. And that model that you have, whether it is black box, gray box, or mathematical model, real grid model, doesn't matter. That should be defining a scope for this parametric optimization that is feasible, real life. That's number one. Number two, the parameters that is generated in the parametric optimization would cover all the nonlinear points of the real system. So the parameters can be generated properly. So I don't know whether I answered your question.
Obviously, sir, actually, nowadays, 10 number of tools are freely available. Okay, one can download, one can customize it, but whether you are getting the good result or desired result, that is different thing.
Very different thing.
That will go after analysis.
That's what matter.
What's going on inside, nobody knows. That is the problem.
So the tool and the solver, what is going on inside, you don't have any control as far as the electrical engineer is concerned, especially, software engineer may be talking differently. But what you are giving in and what you are getting out, you have a control. You can understand. That is where the key importance of modeling. So in this kind of framework, you are actually developing models that are concrete. That is a fallback of the parametric optimization. I'm not against soft computing, by the way. I'm just saying in general. That's a problem of the parametric optimization, because the parametric optimization don't have that framework, right? That model is giving. But if you can develop a good model for that, that also should work pretty well. So the focus that we have to work on, I believe, is not to use tools and solvers blindly, but develop good models so that tools and solvers can be used to solve. And that should be our strength, not the, because I don't think I can understand fully what a Gurobi solver is doing mathematically. Okay, so I'll stop right here. Any other comments, questions?
At least apply process to understand from the basic how this is applied for goods and what this is.
So the toolbox and solvers doesn't do anything with power grid. That is solving a bunch of mathematical equations. So you don't understand anything. This toolbox you are applying to power system through your model. So nobody can apply the toolbox or a solver to the power system without a model. So I am developing the model and I am applying the toolbox. So how these toolbox are used and how this toolbox is applicable, or how the solver is applicable for a power system problem, is that exploration done by you as a power engineer.
When we read the transaction paper, people to understand those things, how they are running, how they are applied. So from the basics, there are any examples of them or any tutorials.
So nobody is applying in the transaction papers or any work that is done by researchers or anybody. Nobody is applying the tools and solvers. They are not applying tools and solvers. What they are using is they are developing models of electric grid. And models of electric grid development is fundamental. What is fundamental to that? Like what we are discussing, power flow, optimal power. That model development is electric grid model. So if you are using a power flow model, that power flow model remains the same. It has got the same fundamental equation. You will be able to see in any paper the same fundamental equation. But what is the difference? Difference is how do you same equation, how do you put it in? I call it casting. Remember, I call it recasting. How do you represent that same equation in a framework that can be understood by the tool and the solver, and using the tool and the solver to solve it? That's all people are doing in any research paper, anywhere you go. Now, why they prefer some tool and solver? There is some advantage that they claim. That advantage, whatever they claim, they will claim in the paper. But that is not the advantage of the tool and solver. That is the advantage of the model that they are developing to tool and solver. So if you look at, if you read all the paper, every paper will have similar kind of equations, voltage equation, power equation. But it is recasted in a different way, meaning same equations, like for example, I square R. I square, you call it L. And when you say L, it's LR. If it is LR, then you can solve it using linear programming. And you solve with this L. And then once how to get I out of the L, they will discuss They'll use some mathematics methods to get I out of L. But at the end of the day, it's still I square R. So whenever you read a paper, stay on the modeling side and understand the modeling. And that's what I was trying to explain to sorry. That if the models are not developed just by parametric, somebody says that, oh, I got a bunch of parameters, and then in particle swarm optimization I got this number, and this number is very good, best. There is no you cannot believe. You say that, well, that is useless, I don't know what to do. But if they say these parameters are based on the power flow, I develop these parameters based on, so then you will, who is doing that? We do. That's what they are publishing, not the tools and so on.
There are some standard already developed. Then we are telling that we have modified some of the parameters and introduced some of the parameters and we have got this answer. This is the correct way of telling it.
It's context specific, so I cannot answer whether it's correct or not. But if you can give an example, then probably I can answer. So, are you saying that you get a parametric set from the real system?
That I can model the what we do. That I see
Hmm.
that in correct equation A, those values what we get constant value B that I get. So whatever we get is different for different flows. And when we simulate it, so if we are trying to bring some more one more parameter and we say that this makes more accurate something like that. I was trying to do that. It was asking about chip model and chip model. Chip model.
Zip model, what?
For particular node, there will be a particular line with not going from ABC right. That
So you are collecting the data from, for example, output from the light bulb, something. You get voltage, current, power, or whatever. You get this bunch of this number. Then you come up with a number for the values for a zip one, and that value that you represent exactly the characteristics of the light bulb. You can actually, and you prove that with the characteristic of the light bulb performance for different conditions, and for each of those conditions, the characteristic of the light bulb can be characterized with the help of this equation with the same value of A, B, and C, which is tuned by some engine. How are you doing it? Because you are proving that with the data set that you are developing, whatever model that you are doing. That modeling that you are developing, the data that you are generating, whatever you are doing, is the contribution. You are not the tool or the particle sum optimization, whatever it does, right? But that tool is valid for that's parametric optimization. That is actually what I was talking about. But that same tool, suppose you use it to find out loss minimization function of an electric grid without having to go through voltage constraints or power constraints on the electric grid, the tool invariably will fail. You can get a loss, but that is not going to be feasible. So, which you will say that, oh, your paper is, you publish something, but it's not of no use because these are the things is not covered. These are the things. So, what is the problem? What needs to be covered? What are the things, details that you need to study there? If you understand correctly and you're solving the problem, yes, that has got a value. That is a paper, not the tool or a solver, right? Because you're borrowing the tool. If you can consider the condition for the tool and solver and say that, well, this tool is useless, that also you need to consider. So, for example, if you have a nonlinear equation, power equation, and you run it through an linear programming, then you are using the wrong box to do the right thing. So you don't have the knowledge that you are using it. So people will say, hey, your method is completely wrong. So that's again nothing to do with the tool and the solver. It is to do with you are not able to model it properly. So any paper when you take it, we don't really consider. There are some things which you cannot even understand, then you do it not properly. For example, solver that you are using. Infeasibility nature of the solver, you don't know. And you put an equation that will make the solver go to the infeasibility nature. And you solve it without knowing. And then you get a result. When you publish it, the person who is actually working on the solver or who are actually knowing about it, he will say that this is not good. What you do, you take that comment and you say, I got a knowledge from him. I will improve myself. And you don't publish, that's okay. because you're getting learning out of that. So there are people who actually does that for a living, right? So yeah, I think you understood the. So you should be focusing on those need what I am, my contribution, and how that helps solve something. That's so we have some time, I guess, right? Half hour or something. Okay, 5:15. You are saying that, well, will we be stopping here? That is something that I want, right? Okay. How many of you are tired? Nobody wants to say that I am tired. If I say I am tired, then you will lose the attendance, right? I mean, whatever is what's 90% or something. So okay, I'll do a trick here. The trick is there is one topic that we need to cover today based on the we are giving you full meal, okay? So sometimes it's overflowing, but we are not going to say that you have, whatever we are offering is different from what is that called, visualized or before. So there is one topic that we need to cover today is modeling of power grid for power flow and time series power flow with DERs. So this is something which needs to be discussed today. So what I'm going to talk, since we have only 30 minutes, what I'm going to talk is I'm going to give you like the same thing what we talked about. What is the problem? What is the need for the problem? And how we can solve the problem with the model that we can develop. So just key aspect. So from here you will see modeling of a power grid for power flow. Do you know it? Yes or no? Did you model the power grid for power flow? Did you run the power flow? Did you model the power grid for power? Or you did not run the power flow? What did you run in the morning? What did you do? Example right now. Forward, backward sweep. What is that? It's a power flow. Yeah. No, I didn't know anything. It will be like more like at the end of the day, you'll say, what did I do? I don't know anything. You did run the power flow. Yes. Did you run the power flow for a transmission network? Newton Raphson power flow equations? Yes, we did. Either you forgot or you're very tired. I would think that it's the second part. It's, maybe you are getting to the end of the day. So we did model the power flow for transmission network and distribution network, right? We did that. I mean, we did do the power flow. We did model the electric grid also. Remember when we did model, we modeled the generators, we modeled the transformers, we modeled the transmission lines. We said the model of the distribution network to 3 lines. Remember the difference? OLTC. So this is not new. Why am I saying that this part there? I'm giving you a specific things what is needs to be. How about modeling of distributed energy resources? Did we model a PV farm with the inverter, 1.2% capacity inverter, reactive power, active power? We did model, on that. So have you done time series power flow? So we did not do time series power flow. So what I'm going to talk in the next 30 minutes, how do you convert, what is time series power flow? How do you convert a power flow to a time series power flow? Why do we need a time series power flow? Where will we use a time series power flow? Okay, you should be able to connect the storyboard. So this is the only thing that is not covered, is missing. And I'm going to focus on DER. Where are DERs located in an electric grid? Transmission system, distribution system, more located. Distributed energy resource. Where are they located? More on a distribution network. Okay. Since the DERs are located on a distribution network, we are going to do focus on the power flow for a distribution network. Okay. Do we know what are the characteristics of the distribution network? Lines. There are two important characteristics of a distribution line. One characteristic, distribution lines are not transposed. Since they are not transposed, what happens? It creates unbalanced nature of the distribution network. Because of that, you have to model the distribution lines in three phase, not on one phase. So we model the distribution line in three phase, and we got a 3 by 3 matrix. Remember or not? We just did it. We got the number. So that is one. Second, distribution lines are going to be multi-phase lateral, means 3 phase, 2 phase. Distribution lines has voltage regulators. Distribution voltage regulator, step voltage regulator. Distribution lines are zip load. Distribution lines has different transformer connections types, Y connection, delta connection. Distribution lines has shunt capacitors. Distribution lines has multi-phase DR with constant power factor capability and voltage control capability. So, if you have an inverter, that same power from the PV coming from the inverter can be used to deliver the active power and the reactive power, not worry about the voltage. Okay, such inverters are considerably called non-smart or not smart inverters, which is delivering P and Q. So what from the PV farm ask 10 megawatt, will PV farm ask 30 megawatt, you deliver that. So such the inverters are model generally called PQ type. Okay, it's like a load. Okay, such inverter or the PV plus load is called net load. Only the difference is that it is a negative load. You agree? Okay, so it's called PQ type. The other type of inverter is basically controlling the voltage at the point by supplying reactive power. And such inverters called PV type. Much like your reactive power that is coming from the. Okay. So I'm going to talk about a method which is not discussed. Unlike forward backward sweep, I'm going to discuss about a method that can be used to solve power distribution system power flow. Okay, and that method is called current sensitivity method. Okay, so in this current sensitivity method, the good news is that you can develop in the distribution system, the best matrix can be divided to develop the Jacobian like this. So this is G11, B1, G12, B2, G21, B2, 2 by 2 matrix. We can develop the Jacobian like that. And the current sensitivity matrix calculates the current error from the power. So if you may recall, we did this just now. Do you remember? What did we do? S load divided by V. Remember that we did? So this is a forward backward sweep and V square divided by C. The only difference is that instead of adding the drop I times Z, remember that we added the drop I times Z and calculated. We don't add a drop with I, we add the drop V square divided by Z. So if you do that, you will get a current. And you can calculate all the currents in here. From that currents and from the sensitivity matrix, you can calculate change in the voltage. In the forward backward sweep, we calculate the change in the voltage by the IR drop. Remember? And instead, you are not using that, you are doing a different way. It's the same thing. This is what I call it as same top we are looking at, but you are looking from a different same equations, right? There is no change in that equation. So this is how you run the power flow model for that specific setup. I'm not going to talk about that in detail. You can compare the power flow for different setup and then so forth. Let me talk about the time series power flow. Okay. So if you look at a power flow, this is important. We're just looking at this. Get a power flow. You run the power flow. What happens if you have a change in the load in an electric grid? What do you do? How do you run a power flow? In a power flow, will you change the loads? When you run a power flow one time, it's a constant. What happens? Oh, is the load constant all the time? Load is changing. What happens if the load is changing? What do you do with the power flow? You run power flow multiple times. Okay. So these are snapshot. We call it take a one power run, take a next power run. So done at snapshots. How many times you do it? Well, depending upon whatever way you do, you wanted to get a peak load, on a light load and medium load, 3 times is good. You run it. With the high penetration of DERs, what is happening is this number has to be increased because the net load, if it is DER plus load is changing, DER is also changing. Correct? So you increase the number. So what you do is, ideally, you have to do 8,760 times in a year, which means one time in 1 hour. That's what people say. That such power flow is called, such study is called 8760 study. You can Google and search and you will see 8760 study. Which means every year the PV is changing, the load is changing. You can mix and match and run for every time. So, static time series simulation is a sequence of steady state power flow conducted at a time step between 1 second to 1 hour. Okay, 1 second to 1 hour. So the first step is take the power flow, run many times, 1 second to 1 hour. Okay, that is not considered as time series power flow or quasi steady state power flow. During a QSTS, the discrete control device like tap changers, voltage regulators, switches and relays can change their state from one step to the other. Right? You have a regulator and one person, it can change the step to other. In the time series simulation, you will include that changes. Okay. Then, so I told you the step. Power flow, multiple power flow done in a year. Time series power flow, which includes the changes of the devices, discrete devices on the power. For example, voltage changes in the voltage regulator. So, no numerical integration, differential equation. Okay, it is just the changes on the discrete time step. Using an accurate load and generation time series data, QSTS, quasi steady time series simulation, can be used to quantify the magnitude and duration of DR impact. Now you understand the difference between time series power flow and the normal power flow? Yes? Okay. So, I'm going to give you an example. Okay. In this example, what we are doing is, we are including a device that changes in steps at different time. Okay. Can you name a controller that changes when the time changes? A controller that changes the voltage, or a legacy device that changes the voltage. There is a device in the electric grid, we talked about it. It's called voltage regulator or load tap changer. It changes the voltage when the time changes. Remember that? We talked about it? Yes. So what happens if you do multiple power flow without taking a regulator? At one point, power flow is done. Next point, power flow is done, taking care of the voltage. But the regulator is changing the voltage. Do you need to consider that or not? Ideally, yes. Otherwise, your power flow solution is not correct. Okay. If you consider, then the power flow will become quasi steady state power flow. We are considering operation of the legacy device. So, I cannot go in detail about it, but because of maybe time, but this is a representation of a control of a transformer, tapped transformer. I should, I think, explain a little bit in here. So this is a transformer high, transformer low, a variable transformer, and line is connected, and this transformer is tapping the current through PTs and CTs. Everybody know PTs and CTs, potential transformers and current transformers. So it's tracking the power through PTs and CTs, and that power is going to go through voltage relay loop, and it is trying to look at the voltage, and that voltage is here to change the tap. This is an operation of the load tap changer. Okay, so we talked about the load tap changer. What is a load tap changer? How it works? It looks at the load and then tap the transformer voltage. Okay, so now you have a question. I think we discussed this. We look at the load, meaning you're looking at the drop in that node and then tap it. Okay, so this drop is generally called uh, line drop compensator. Okay, so what is a line drop compensator? It looks at the line of the electric distribution network and look at the point where the voltage needs to be controlled. So I think I draw a voltage drop equation from the substation to the last point, right? If I want to control that last point, I cannot take the voltage at this next to the transformer. I have to take the voltage or the drop somewhere else, the current on the load. So normally what you do is that this line drop compensation will look at a point on the distribution network somewhere 2/3 from the substation. 2/3, 1/3 is a thing. So you go to 2/3 point and then take that load connection from there, or load drop from there. So that is represented in the regulated point, and then CT measures that, calculate in the form of a drop, and then regulate the voltage. Okay, so it's a compensator, impedance settings, voltage level settings, bandwidth settings, and time delay setting. These are the 4 things that happens on the regulator. So what we do is we do a model of this whole thing in the power flow, and you include that model of that transformer along with the power flow. Okay, so what we did now, we did the power flow model convert into time series power flow model. Okay, and these are some of the results. This is the result from the real model and the field device. So where it is used, if you look at a time varying load profile for a load, and you look at the initial tap for the LTC and the final tap for the LTC that is changing, the voltage profile each phase of the node 8 of the 123 bus, you can see this is with no regulator, this is with regulator. So the voltage with no regulator and voltage with regulator, you can actually see how much voltage changes. This is not a, this is not a new control that is doing the control of the regulator. This is just studying what is happening in the electric field. The regulator is moving, it is also getting the information what the regulator is doing. We need that, otherwise the power flow is not complete. So that's what it's trying to do. You can see that power flow in here, I mean the voltage in here, which is with the regulator. This is one application. What's the second application? Let's assume you have a PV farm changing. The LTC is tapping. You want to look at what is the voltage with the LTC tap. You can look at the voltage profile with the LTC tap. Okay, are you following? Yes or no? Transformer is tapping, you are getting the model considering the tap of the transformer. And then you can use to see how much the DER voltage changes and how that can be studied. So I'll stop right there. Probably that's it. I think people started looking at the face, punching out a little bit. So, having said that, I hope you got a glimpse. Quasi steady state time series power flow means, along with the power flow, including devices that is changing in a step change between times. Okay. So, you model the device, include that in the quasi steady state power flow, which represent the real system when the input changes. Any device can take. Any time dependent device that is changing. So in battery operation is basically, battery is considered as a time dependent constraint. So it actually changes with respect to the operation. You just include that. DR, you can include that. You can model any time dependent device, not the very fast changing, because that needs probably integration or differential equations, or but it's like minute range or that kind of changes that happens. You can. So such models, development of such models are required. It is even required now because it's PV changes in. It gives you a realistic path. So there is one I couldn't, I forgot about it, but I will put that. There is one article that we published on this in a transaction or some journal. You can read that. And I'm not saying that we published great, but that's one example. There are several people, doing things like that. But the idea is, when you model it, you have to be realistic, and then you have to include that part there. And one example that we showed is a transformer tap. Basically, that's a we from reactive power contributing to change in the voltage. You can include that slow, not fast. So you don't have to do a cumbersome, differential equation or optimization algorithm. Nothing. You can just do this for a small algorithm and then try to see what happens in the real field. Probably have enough for today. So tomorrow when we come back, we will start now moving from moving from steady state condition to dynamics a little bit. So the dynamics will be, and the time dependency and all that will be the next 2-3 days. Our goal will be 2 days rather. Last day I think probably will cover newer topic or advanced topic or something. But that's our goal for tomorrow. I hope you are following the time dependent nature. And keep us posted if you have any questions or any comments. You want some area that needs to be, I think on Friday talk, we can also do a look at some specific questions if you may have on some areas that you think we should cover.
Sir, there will be examination on Friday.
There is an examination also on Friday. So keep that in mind. If you don't do well on examination, that will be bad. So you have to do well on the examination. That's another thing. Oh, I am not going to give you well, I think we should give you that problem, right, for the homework assignment.
Sir, assignment you can give because this is one of the parts of this course. So one assignment, sir, you can give them.
So what I will do is
That can be accessible, like that we can assess and.
Correct. So what I am thinking is that I will give you these few slides that we have done for the forward backward sweep problem.
Assignment is mandatory actually, so you all will try from your side to complete it, and then again we will meet tomorrow for that.
Do you want the problem again, or you got all the numbers you want to solve? Do you want me to formally give a question with all the numbers again to you, forward, backward sweep, or you already got the number. You will solve it. Same number. You know what a number means, like impedance. And how many of you think that I should give that problem again? Three. Raise your hand. 1, 2, 3,
Here also.
2, 4, 6, 8, 10, 12, 14, 15. 15 failed. It's more than 15 here. More than 13 here. You need a 50% mark majority.
Is it clear regarding the assignment? What assignment sir has given? Any confusion?
Okay, then why do you need? I'll send it. Uh, uh, no, that's it. Yeah. So that's it. So I'll send you the assignment to you. You can broadcast, right? I'll give it to you, and then it'll take 1 hour. I'll put this back into the Word file, and then I'll put it here. Maybe 1 hour. I have to prepare. I have not. It's in the slide.
Okay. Okay.
And then you can send it out.
Okay.
Okay. Thank you all.
Thank you, sir, for this nice session, because you have focused on so many things regarding the optimization, and I think you all have benefited with that. Again, we will meet tomorrow with the new lecture topic, and we'll proceed with that. So, meantime, you will just do the assignment from your side, all right? And then, if you will have any confusion, you can clear in tomorrow's tutorial, or sorry, in lecture class itself. Thank you. Thank you very much.